around with this when I was a student. I won't say how long ago it was, but we had pretty limited computer power, so you couldn't do much of a simulation. So no doubt we'll learn about the state of the art tonight. So welcome. Oh, the other thing he mentioned is that he's also a model railway enthusiast as well as a mathematician, so an interesting combination. So thanks very much, Philip.
Thank you. Before I get started, I'd like to encourage you to ask questions during the talk rather than at the end of the talk. The reason I mention that is I used to be a volunteer instructor of bushcraft and outdoor first aid for the New Zealand Mountain Safety Council. And as part of my training one time, I had to do a risk management course. And part of that course, there was a scenario. And halfway through the scenario, I said to the instructor, I want to ask a question. So I did the timeout signal. He said, no, you can't stop. You have to wait to the end of the scenario before you can ask a question. So I got to the end of the scenario and I had forgotten my question. And 7 years later, I still cannot remember the question. So I encourage you to ask the questions as soon as you think of them. So my research area is looking, as you can see from the title, doing simulations of the solar system. Well, why would we do simulations? Why not use algebra to solve the equations? And the simple answer is the equations are too complicated to solve exactly using algebra, using x and y. You have, that's the sun there, and we have a body, a single planet revolving around the sun, then you can solve the equations, the motion of the planet exactly. But if you put in a second planet, then in general you cannot get the exact solution algebraically or mathematically. You have to do some sort of approximation. And there are various ways of doing approximations. And the way I look at is something called n-body simulations. So there are approximate techniques, but they can be very accurate. And what I'm going to start off with is a very simple application of the methods I use. Go upside down this way.
Oh, you may have
Okay, so Auckland's at the top, and this is my hometown of Marston here, and about 4 times a year I drive down to visit my mother, auntie and my sister there. And we'll assume it's 600 kilometres. I go via National Park rather than going through the desert road, so about 600 kilometres. And let's assume I'm sitting there in Auckland, there's no traffic, it's maybe 3 o'clock in the morning, and I'm doing 100 kilometres an hour, 600k. How long is it going to take me to get to Marston? That's not supposed to be a hard question. So 100 kilometres an hour, 600 kilometres, that's a pretty good estimate. How 6 hours, that's right. So how did we get 6 hours? It's common sense, yes. You know how to get 6 hours. So another way of looking at that is to say the distance I travel is my speed, which is 100 kilometres per hour, times the change in time. So we have 6 hours. So I'm going to call that interval of time the time step. So what I've done is taken the speed, multiplied it by the time step, and that's given me the distance that I travel. Now we know that that estimate is not going to be very good. So how could I get a better estimate of how long it's going to take me to get to Marston from Auckland? What can I do? So the first thing I attempted was I'm up at Auckland, I'm doing 100 kilometres an hour, I know it's 600 miles, therefore it's going to take me 6 hours. What would be a way of getting a better estimate when I can arrive, so I can text my mother to let her know when I'm going to arrive? What else? What could I do? Google Maps.
Variable speed limits.
Sorry?
You need to type in the variable speed limits because the speed limit's not always 100 k's on the
That's
roads.
right, yeah. So the quickest I've done is 7 hours 20, and that was on Christmas Day. And the slowest has been 9 hours 55 minutes. Not that I keep a track of those details. Okay. Well, a thing I could do, that time step of 6 hours is too long. As you rightly said, there's all sorts of things that can happen during those 6 hours. It could be roadworks, there could be RVs, there could be trucks, all sorts of things. So if you want to get a better prediction, you need to predict a shorter time into the future, if you like. So what I could do is I could get down to, say, maybe tie happy here, and I've got there in 6 hours, and then I'd have a better chance of predicting exactly when I would get to master, because I'd only be predicting over a shorter distance or over a shorter time. So just to summarise what I've said here, we can estimate how far something's going to travel by the speed it's going at the moment and how far in the future, it's a time step you're trying to predict. But the further you predict in the future, the less accurate your prediction is going to be. So you want to have small time steps. You want to predict how far you're going to get and then predict again. You keep on predicting using smaller time steps. So that's a simple example. Are there any questions about that? So work out how to use it. Right.
I think,
Oh, it's the wrong way. Upside down. Okay. I'm left-handed, that's why. Okay. Okay, so this is a harder problem here. We're going to try and estimate how far this drag racer goes in, say, 5 seconds. And this starts from a stationary position. And if I tell you how fast it's accelerating, the number of kilometres per hour as the speed is increasing, how could you work out how far it's going to go in, say, 5 seconds? It's likely to be around about a quarter of a mile. So here I have the speed that's changing. In the previous example was assuming I was driving at 100 kilometres an hour, and from that I could try and estimate how far I would travel in 6 hours. Here it's more complicated. I don't know the speed, I know the acceleration. So how do I work out how far it travels in, say, 5 seconds? So this is a more difficult question. Think about you're at a traffic lights and you accelerate away. How would you work out how far you can get in 10 seconds, or whether you can get to the next intersection before the lights change? So how do you do that? How do you use acceleration? Because here the speed is changing. It's important you understand the idea of acceleration because we need it for the simulations of the solar system.
Is your acceleration half
Sorry? Yeah, that's right. So you're using the kinematics from high school. Yeah. So another way is, which is effectively what you're doing there, but is from this acceleration you can work out the speed at a certain time. So if you're accelerating at, say, 10 kilometres per hour, very slow acceleration, then you know after 2 seconds you would have be going at a speed of 20 kilometres per hour. So from the acceleration you work out the speed, and then from the speed you work out the distance travelled. But you've still got the same idea. You're trying to predict into the future. You're taking a time step. So you use the acceleration to get your speed, and then from the speed you get the distance. But it's an approximation using these time steps. Okay, which way was this way? Right. Okay, now we're getting something that's a bit more realistic, and we're going to be talking about the acceleration. So this is looking down from the North Pole of the solar system. You can see the planets there, I hope. And the white dots are the asteroid belt. So the green dots are called the Greeks or the Trojans. What's special about the green dots there? So the Greeks down here, the Trojans. What's special about them? Anybody know?
The L4 and L5 points,
Which are what?
Lagrangian points,
Yes.
where the gravity of the Jupiter and the Sun are pretty much equal.
Okay. And what is the angle?
orbital speed is
Yeah. So if you think of this line here and this line over there to the centre, what's the angle between them? 60 degrees, that's right. So this is just by the way, but these asteroids are in front of Jupiter and they move around a bit, but generally they're about 6 degrees in front, and the Trojans are about 6 degrees behind. Okay, now just look at Jupiter there. It has almost circular orbit. I'm going to assume that it is a circular orbit. So if it has a circular orbit, it's moving at a constant speed. But you think, well, that's easy, then I can work out how far it travels. Right, if I know the speed it's travelling, and I know its orbit here, it's a circle, I can work out exactly where it is after 1 year, 100 years, 1,000 years, or whatever. But if you just know the acceleration, that's all we're going to know when we're doing these simulations. We just know the forces, the gravitational forces and other forces on these bodies. We don't actually know the curve here. So we have to work out from the forces what direction this planet is going to move. And it's in 2 dimensions now. So we don't have the speed, we don't have the position, we don't have the orbit. All we know is the acceleration. And And it's more complicated than that drag race because we're working in 2 dimensions and not in 1 dimension. Okay, if you think about a car going along straight, there's no forces on you. You go around the corner, if you go around quite sharply, your body's going to be pushed to the outside of the car, and there are forces that are keeping the car, making sure it goes around the corner there. So there's an acceleration involved there. So although Jupiter is going around this orbit at essentially the same speed no matter where it is, it's being accelerated all the time because it's being curved around all the time. So the sun is pulling on it and it's changing its direction. So although it's going at the same speed, it is being accelerated around this here because it's being deflected inwards. So everything is built around acceleration. So that's a key point. So we're going to be working with acceleration, and then from the acceleration we get the speed, and from the speed we get the position, and we're always predicting into the future. We want to get accurate predictions, so we're going to be predicting just a few days or a year or something in advance. Okay, so in order for me to do these simulations, I need a mathematical model. And what goes into a mathematical model? So I'm going to list a few points here. And probably the most important things are the bodies that I'm trying to simulate. So here are some characteristics I have to think about each time when I'm writing down a mathematical model. And they're pretty standard, the models. The first one is, do I use real bodies or do I use hypothetical bodies? Is there any ideas about that? Any opinions? Should I use real bodies like the planets as they are now? Or should I just make up some hypothetical bodies? What's the advantage of using the real bodies, or the real bodies, as opposed to hypothetical ones? So why would I want to use real bodies?
Check.
Yeah.
Presumably a real body is affected by tidal
Yeah.
forces, whereas like a hypothetical point wouldn't be.
Yeah, I'm getting to that in a minute. But
Oh.
so it's good that you're getting here. You can take over the lecture if you want. Right. Okay, so why would I use a real one? That's because I'm trying to model the solar system. So why make stuff up? Why not just use the real bodies? The disadvantage of using the real ones sometimes is there's been a selection effect. You don't know what's happened well in the past. All you're seeing if you use the real bodies is the state of the solar system as it is now. So as I said, there's a selection effect. If you use hypothetical ones, you're free to choose these bodies which you think as they might have been 100 million years or a billion years ago. And you're eliminating some of the selection effects. So there's a case for both, using real bodies, and NASA, for example, with the mission plannings, with their DE-405, ephemeris, they will be using real bodies and have very detailed models. But if you're trying to understand the dynamics of the solar system, then it makes sense to use hypothetical ones because you don't have the selection effect. Okay, how many bodies should you have in your model? Right, where you say, well, if you're using real ones, you have exactly the same numbers of real ones. That's true. If you're using hypothetical ones, you ask a computational astronomer, so n is the number of bodies, how big do they want n? And you say, with n equal to 1,000, all right, you have 1,000 bodies, now I want double that. So you try 2,000, I want double that. They keep on doubling it. N is never big enough. The n is the number of bodies when the computational astronomer is doing work. So I'm going to present results here for 500,000 bodies. That's my biggest simulation up to now. So this number, you make it as large as you possibly can if you're not dealing with real bodies. Okay, the shape, as you were talking about, the tidal effects and that. What's an obvious shape for a celestial body? Sphere, that's right. So the Earth is not a sphere, what is it?
Spherical.
That's right, so what is an inflate spherical?
It's just the word sphere, I guess.
Okay, so one way of looking at what the Earth is, you just get some dough and you make it into a ball, and you put a knitting needle through the centre. Probably younger people don't know what a knitting needle is. But anyway, you put a knitting needle through the dough and you start spinning it. What's going to happen to the dough? So you've got this here, and the needle's through there, and you start spinning the needle around like, what happens to the dough? Yeah, it sort of squashes this way. So that's what's happened to the Earth. You think it was a super cool liquid to some extent. So its distance between the two poles is less than the distance across the equator. Okay, now you don't need to worry about that if you're a long, long way from the body. If I'm over here and that's the sun over there, then I can assume for all intents and purposes that it is a sphere. But if I'm up close, and as happens with the sun, it's slightly squashed this way, then the gravitational field may be different up here than it is out here. So if I'm after a really accurate model, then I may have to assume that the sphere is, or that the body is not a sphere. In fact, it's a blade spheroid, as we said. Okay, the size and the mass. Now, a lot of the work that people, computational astronomers do, they don't worry about the size of the body. They specify the mass, well, they're going to come back to that in a minute, but they don't worry about the size. They just say it's a point body. It has no finite dimension. That may seem strange to do that, but in a lot of situations you can assume that the body has no size, it has a mass but no size, because you're not worried about collisions, for example. And the other thing you have to think about is, where do you start the simulation? What do you assume for the initial position and velocity of the bodies? Now, if you've got the real ones, you can just go and look up on horizons or JPL ephemeris, at least for the last few hundred years. But let's say you want to simulate the motion of the planets 100 billion years ago. What are you going to do? What are you going to assume for the initial position of velocity? And then what about when you go to the hypothetical ones? What are you going to assume? Where are you going to start in the simulations? These are non-trivial questions that computational astronomers have to worry about. And you get different people having different ideas. So you can get 10 computational astronomers in a room and you have 11 opinions as to what the initial position of velocity should be. Often. So anyway, this is all part of the mathematical model. You have to think about that. And people have done, right. People have done that. Okay. Now we've sorted out the bodies. Now we have to think about the forces you're going to have in your model. So the obvious one is Newtonian gravitational forces. So that's the apple falling out of the tree, hitting Newton on the head. Relativistic forces. What are relativistic forces? All right, tell me. It's worth 5% of your final mark.
It's a quantum apple hitting Einstein on the head.
Is that right? Yeah, that's right. It's got on Einstein. So is it special relativity or general relativity? Yeah, there's more likely to be general relativity, yes. Okay, non-gravitational forces. So what's an example of a non-gravitational force? I've never used these in my models, but some people do. Certainly NASA does in their accurate models.
Solar wind.
So?
Solar wind.
Yeah, radiation. You have very small bodies, that's a good one. What else? What about comets? What happens to comets when they get closer to the sun? Besides falling apart.
Material boils off.
Well, that's right. So that's going to change their mass, for example. Another example is if that's the sun over here, and this is a small body. It's going to be hotter there than it is there, and it rotates. And when it rotates, it gives off some of its heat as energy, and that changes the momentum. And you may think that has a small effect, but NASA actually have to allow for that in their mission planning. So there are examples of non-gravitational forces. Okay. And here is a very important point from a pragmatic point of view. Let's assume we've got about 50 people in the room here, and every person is interacting with every other person. So you two are interacting, and then you're interacting. So how many possible combinations of interactions do I have if I've got 50 people in the room? Lots, yeah, that's a good answer. Okay, I've got so person 1 interacts with how many people then? If there's 50 people in the room? 49, okay. Now, now let's look at person number 2. Now we've already allowed for their interaction with number 1. So how many other people does number 2 interact with? 48. So I think you can see a pattern now, 49, 48, all the way down to 1. So that is something like 50 squared over 2. So that's 1,250 interactions you have to worry about. And every time you have to model interaction, you have to do your computer simulation and soak up a bit more CPU time. And you'll see in maybe 10 or 15 minutes that CPU time can be significant. So this is what I mean here. You look at all the interactions. So in this room, there'll be about 1,250 interactions. There's another possibility that applies when a lot of the bodies are very small. And what you do then is you ignore the interactions between the small bodies. So for example, if you're modelling the sun, the planets and the asteroids, except one or two, are a lot smaller, they're a lot less massive than the planets, you can assume that the gravitational interaction between two asteroids is insignificant compared with interaction between two planets. Right? Because the asteroids are far less massive and the acceleration is going to depend on the mass. So this is the big simplification. You also assume that the small bodies, so the asteroids, do not affect the motion of the large bodies, the planets and the sun. So the planets and the sun affect the motion of the asteroids, but the asteroids do not affect the motion of the planets and the sun. That's an approximation. So what does that mean? So we're ignoring all the, so I'm the sun, I'm the big guy here, and you're all the asteroids. We're ignoring all the interactions amongst yourself. The only interaction you have to consider is with me. So how many interactions do I have if I've got 50 people in the room, under that scenario? 50, that's right. I've gone for 1250 to 50. That's a great simplification of the model, but it works well if we know that these small bodies are far less massive. We're talking orders and orders of magnitude, less massive than the big ones, the sun and the planets. So just to make that point a little clearer, so it's the same diagram, I'm recycling here to save money. So just imagine we've got Jupiter interacting with Mars. So Mars and Jupiter, they're far more massive than all the asteroids here. So what we're assuming, or what I assume in most of my simulations, is that I can ignore the interactions between every pair of asteroids here. And you can see there's a large number of asteroids there. The only interaction, the only forces I have to worry about are between planets and the sun, and between planets and also the effect of the planets on the asteroids. I ignore the interaction between the green dots, and I also assume that the green dots don't affect the motion of the planets. So that is the big simplification there. Okay, so we've got our mathematical model, and now we've got to think about a numerical method. So what I mean by a numerical method is essentially what I described when I was talking about how long it takes me to get from Auckland to Marsden. So you have information about, so the initial information, initial velocity and the position, and you try and work out where the position, where they're going to be 5 days from now, 10 years from now, 100 million years from now. So that's the numerical method. It enables you to get from your starting point to the position of velocities somewhere in the future at different points. Okay, so you're a mathematician like me, and what would be desirable features of this numerical method?
Cheap.
Cheap. So what do you mean by cheap?
Fast.
Fast. So what do you mean by fast? So what does fast mean?
Well, you're using computers, so you won't get it done quickly.
Right, that's right. So you want as little computer time as possible. Now, there's an ambiguity there, we'll get to that later on. Okay, so we want it to be fast. Cheap can mean something else. Cheap can mean that the numerical method is easy to implement and get right. So we won't worry about that. Okay, so we've got it fast. What else do we need to worry about?
Accuracy.
Accuracy. Why do you want it to be accurate? I think that's a good idea.
Well, if you're trying to predict what has happened in the past or in the future, then it's not accurate, then the result isn't very worthwhile.
It's out to lunch, in fact. Yeah. That's right. Okay, so if you weren't worried about accuracy, you could just write your program so it always prints out the number 42, no matter what the problem is. Okay, so it's going to be fast, it's going to be accurate. Those two things are contradictory, pretty much. If you want it to be accurate, you're going to have to spend extra time. If you want it to be fast, you have to give up on accuracy. So there's a compromise to be made here. Any other resources or any other things about numerical methods we might need to worry about? Adaptable. What do you mean by adaptable?
So it can be used to model different systems?
That's right, yes. So I've written a reasonably general piece of software. But there's a difficulty there is the more specialised the software is used, the faster it's going to be. So there's another trade-off there. And there's also this notion that if you're trying to make it very general, then it's probably going to take longer to write. So there's a number of trade-offs. Okay, so we've got fast, we've got accurate, we've got adaptable. So always applied in many different situations. Okay, any other ideas? Okay, what other computer resources can you worry about? So we've spoken about CPU time, so computer time. What other resources do we have to worry about? If people have got iPhones, I'm continually battling, or smartphones, continually battling with the following resource. So what is that?
Memory.
Memory, that's right, yes. And memory is very expensive now on supercomputers. So you have to think about how much memory it's going to have. And there are two aspects to memory. There's the inside the program itself. It has to store the positions of the, position velocities of the bodies. So that's going to take up memory. It's like the core memory of the computer. There's also the fact that you actually have to print some numbers out from the computer. There's no sense running a program, as some of my students do, and have no write statements, so they have no output from it. It's not particularly useful. So you have to print all this information out. And it's very easy to get 100 gigabytes of data.
You said at the beginning that you wanted to use 500,000.
Yep, that's right.
Yeah, so if you're worried about computer power and stuff, maybe you shouldn't use so many.
However, the more bodies you have, the more accurate you can. You'll see that. I'll illustrate that, I think, a bit later on. Right. Yeah. Anyway, it's a game. You're trying to outdo the other person by having more bodies. Okay. But you're right. You want to minimize the number of bodies subject to having sufficiently accurate results. Okay, so it's also printing out the data that's very important. I'm having that difficulty at the moment. Normally I print out the information every 10,000 years in my simulations. So that might only require 100 megabytes. One of the people I'm working with is at UCLA, wants the data printed every year. So it's free, and so he wants it done for the 500,000 bodies. That ain't going to happen. Not if I print it every year, because I won't have enough space. That's terabytes of data, and then I have to go through and post-process it. So you have to think about also the disk space, hard disk space. So let's see how you did. Oops. Okay, accurate. Okay, I said efficient. This is different from being fast. So what efficiency means is that for a given accuracy, it's as quick as possible. You don't want to give up accuracy. Some computational astronomers do give up accuracy and want to have the program faster. I maintain that you should fix the accuracy you want, and then you make the program as fast as possible. But you must, this is my belief, you must always not sacrifice accuracy. If you decide beforehand you need so much accuracy, then that is a constraint that's fixed, and then within that constraint, you try and make your program as fast as possible. So that's different from being fast, because as I said before, you just get it to print out number 42. It's going to be fast, but you've given up on accuracy. So all of my work, I specify the accuracy beforehand, and then I try and make the program as fast as I can without sacrificing that accuracy. Reliable. These methods, as I've mentioned before, are doing approximations. Sometimes these approximations are going to break down. So you want the method to be able to detect when it's at a point that the approximation is broken down. So you want the method to be reliable. It needs to be able to do a soft crash. It needs to detect, no, this approximation is not going to work here. For example, an asteroid has got extremely close to a planet. There's big accelerations. The asteroid is moving very quickly. It's changing direction very quickly, and the approximation is going to break down. So you need to know, well, you need to have confidence that your method will be able to detect that situation. It stops. It comes back to your program calling it and says, I can't go any further because of the following reasons. There's no sense having unreliable results. Okay, near chaotic motion. So first of all, what do I mean by chaos? I don't mean the traffic is chaotic. What's a slightly more scientific definition of chaos? Anybody know? Besides Bill? I can see he's busting the tongue. Okay, so what does chaos mean? Anybody know? So I'm looking at a more scientific definition. Okay. The weather is an example of a chaotic system. Unpredictable. What do you mean by unpredictable?
You can't tell one day it might look as though it's going to rain, and they tell you it's going to rain, and then it doesn't rain.
Yeah, so
it's like you can't tell whether it's going to be reliable or not.
Right, so what is a slightly more abstract way of saying that is if you change the initial position, so you change the temperature here in Auckland by 1 degree, then several days down the road, the weather has changed dramatically. It diverges exponentially, sort of a mathematical term. So small changes in your starting position can lead to big changes in the weather. So typically the weather is regarded as being predictable maybe up to 7 days. Here in Auckland it's probably about 7 hours from what I've seen on the weather forecast. Okay, so what does that mean? Well, let me give you an example. When I first started doing computational astronomy, if something is near chaotic means it's well, obviously not chaotic, but small changes in the starting position can lead to large changes. And I did this simulation when I was a greenhorn in computational astronomy, and I got a set of results, simulation, 1 million years, that's right. I then changed something in the 16th decimal place. So essentially I changed the position of an asteroid in the 16th decimal place, did the simulation again, and the asteroid was on the other side of the solar system. It had moved 60 astronomical units over a million years. So there's an example of something that's near chaotic or chaotic. So what does that mean? It makes it very difficult. You're always going to have errors in your approximations, and if your calculations are so sensitive that these errors can lead to really large changes in the positions of the asteroids, how are you going to be able to use it to make predictions? So there are some methods around that supposedly can handle chaotic or near chaotic motion. They can still come up with sensible predictions, even though you've got these solutions that are diverging wildly, exponentially. Another possibility, and this explains why I have 500,000 bodies, is I can take an average over a large number of bodies, and that will help improve the predictions. So that is one justification for having a large number of bodies. Okay, storage requirements, I think we decided, except when you're putting stuff at hard disk, that it is not much of a constraint. Oops, I turned it off. Okay, let me just go back to see if I have one before that. We've got that, right. Okay, so how do we make a solution more accurate? And if you go back to me driving from Auckland to Marsden, you have a smaller time step. So instead of having a time step of 6 hours, I can have a time step of 3 hours. But that means I have to take twice as many steps. So if I want to predict a solution from 24 hours from now and have a time step of 6 hours, that means I have to take 4 steps of 6 hours to get to 24 hours. If I go back now and use a time step of 3 hours, I have to do 8 steps in order to get to 24 hours. And every single operation on the computer is going to take a finite amount of time. So I can do twice as many steps. In other words, I have half the time step of half the size. It's going to take me twice as long. Okay, so I can get more accuracy by having a smaller time step, but I take a hit on the CPU time. And there's something else that changes. So what I've done here is I've taken a very simple problem, sort of problem I teach my second year students, and I know the solution, I know the true solution, the algebraic solution to that, and I integrated from 0 years to 1 year. That's sort of a very simple problem. And the first line of numbers there, I took 10 steps. And since I know the true solution, I can work out the error in my approximation. So I know the true solution, and then I got a numerical approximation. I did a simulation, and I took 10 steps. Then I went back, and the end there is the number of steps. I went back and I did 100 steps. So that means the step size, or the time step, was 1/10 of what it was before. And how much is the error gone down? Someone told me that. So we're looking at the second line here. So how much is the error? So that's the error when I had 10 steps. So how much smaller is it now when I have 100 steps? 10 times, that's right. Then I went back and did, these are real experiments by the way, I'm not making up numbers. I went back, as I often do, anyway, I went back and did 1,000 steps. So now the step is 1/10 the size of what it was back there, and the error's gone down by another factor of 10. Well, this is great. I'm using more CPU time, but at least I'm getting more accuracy. 10,000 steps. Now the zeros appeared there, this is good. Now when I went to 100,000, I didn't get the factor of 10. I only got about a factor of 3. And here it went up by a factor of 5, and here it went up by a factor of 600, which is not particular. So what is going on there? What's causing that problem? Okay.
Maybe division by smaller and smaller numbers leads to more inaccuracy.
Yeah, and that can certainly happen, but it's not happening here. So what is happening here? It affects all your lives. It affected the Vancouver Stock Exchange Index, and people lost millions of dollars, probably billions of dollars, back in 1984 or something. So what is happening here? What's causing this problem? Some of you should know, surely.
Average.
Average? No, no.
No.
Rounding errors? Rounding errors, we said that. Good. So what do you mean by rounding error? No, I'm not trying to put you on, yes.
The number of zeros.
Number of zeros, yeah, the number of digits that your computer uses. So your calculator might only use 8 or 9 digits. Texas instruments had a GAR digit, so you might get 10 out of it. On this particular computer, I only had 8 digits of accuracy. And you might think 8 digits of accuracy is going to be sufficient, but it isn't, because think of the number 0.33, one third is 0.333, and you cut off some of those extra 3s. You think, well, it's only in the 8th decimal place, I don't need to worry about it. You've got to remember these computers are extremely fast. If I run them for a year, so some of these simulations take a year, if I run them for a year, they're doing trillions of calculations. And if you make a little error on each calculation, then the accumulated error is going to be very large. Now, I don't use 8-digit arithmetic in my simulation, we use 16 digits. But even so, I can lose maybe 13 digits of accuracy just because of round-off errors on a long simulation. And you have that, so round-off error is always present in everyday life because calculations are not done to an infinite number of digits, they're done to a finite number of digits, but usually you don't need to worry about many calculations. But here, I'm doing trillions of calculations. So that's something I have to contend with. Okay, making faster. How can we make it faster? Well, let's make the time step larger. If we make the time step larger, then I lose accuracy. And there are plenty of computational astronomers who would make the time step larger. I don't do that. I specify beforehand what my accuracy is, what I require it to be, and that is a hard constraint. And then I try and make the method faster. Another possibility is to simplify the model. So before I was talking about 2 types of interactions where everybody in this room interacts with everybody else. And then the other possibility is where you only interact with me. So that's the simplification of the model. You can go even further and say that the people in the back of the room don't interact with me because they're too far away. So you can simplify the model further. But what happens when you simplify a model? What could happen?
Lose accuracy.
That's right, yeah. So you have a modelling error. So you've got 2 sources of error. You've got the error in the model, and then you've got the error caused by your numerical method. So you have to be very careful there when you simplify the model. In fact, you may change the solution fundamentally, and you get the totally wrong conclusions. Okay, now another possibility is to speed up things, is to remove the small bodies, so that's the asteroid. So partway through the simulations, an asteroid might collide with a planet or the sun. I'll show you some data of that in a few minutes. So you remove it from the simulation. What do I gain from removing from the simulation? Why is that a good thing from a CPU time point of view?
Less things to calculate.
Less things to calculate, yes, that's right. Okay, so we'll see an example I'll do in a few minutes that there was quite a few collisions. Ejection from the solar system. So what do I mean by ejection from the solar system? Okay, you won't necessarily know based on your background knowledge, but I was just wondering what you thought. So when I say ejection from the solar system, what am I saying?
Gets put into an orbit that doesn't come back around the sun.
That's right. Now that's an interesting
Things
point
that
you
are
mentioned there. So it's got terminal velocity from the solar system. Yeah. Another possibility, most computational astronomers just say, once it gets out beyond 50 AU, I can forget about it. There's probably only 3 of us, or the one group, who also use the condition you have. Not only must it be 50 AU away, it must also be on an outward bound orbit. So it must have reached terminal velocity for the solar system. Okay, parallelism. So are there any other questions? Or any questions, by the way? Remember, you don't ask a question, you won't know. No questions. Okay. So what do I mean by parallelism? computation I'm talking about.
You do as many computations at the same time on different CPUs.
That's right, yeah.
So you cut down the amount of elapsed time.
Elapsed times, that's right. You don't cut down on the total number of calculations. With parallelism, you're doing, and I'm going to illustrate on the next slide, you're doing some calculations on this CPU or this computer or CPU core processor, whatever you want to call it, and you're doing the remaining over here. So you're still doing the same number of calculations, but you're doing it half the time. So it's human time here that's important. Now I said that you're doing the same number of calculations, you're just spreading over two computers. In fact, the parallelism I use, I'm doing a little bit more. The parallelism introduces some extra calculation, I'll show that in a couple of minutes. But the elapsed time goes down tremendously. Now parallelism can, in the real life, actually reduce the amount of work you have to do, the total amount of work. And I was raised on sheep farms in the Warwick and the Manawatu, and at hay season time, you'd load the truck up with 100 hay bales and you drive it over to the hay shed. And if you're a single person, you climb up on the truck, you toss down 6 or 7 hay bales, you have to climb down off the truck and you go and stack them, and then you get back up, climb up on the truck and throw down a few more hay bales, and then you have to go and stack them. If you have 2 people, which often happen, you have one person on the top of the truck throwing down the hay bales, and then the second person in the hay shed, and they're stacking them. And you eliminate the need for that person to climb up and down the truck all the time after a few hay bales. So there's an example in real life where parallelism actually reduces the amount of calculations you have to do. But in these computer simulations here, we're doing the same amount of calculation. In fact, we're doing a little bit more, but the elapsed time, as Bill said, is reduced. Okay, so how do we do it? And the only simulations I'm looking at in this talk are those in which I ignore the interactions between the asteroids. So in other words, I ignore the interaction between you. So the only interaction with me. So what you do is you take 2 copies of the solar system. You notice how I've reused the same diagram now? I should get ready for this. Okay, anyway, so it's exactly the same diagram. And this is the first computer or first processor over here, and this is the second one. So on the first one, I put all the massive bodies. In other words, I put the sun and all the planets that I'm considering. Different simulations are going to use different planets. And then I draw a line down the center here, and I eliminate half the asteroids. So on this processor, I have all the planets and the sun, but I only have half the asteroids. I can do that because asteroids are not interacting with one another, and they're not influencing the planets. And over here, I repeat the sun and the planets, and I have the other half of the asteroids. So I'm actually simulating the motion of the planets twice. So that's a little wasteful, but I gain for the fact that I don't have to sit around so long. We'll see just how long you have to sit around. So this is an example of parallelism. Now I don't use 2 processors. The example I'm going to show, I think it's on the next slide, had 500 processors. So I took 500 copies of the solar system, and on each processor I put this sun and the various planets, and I took, this has 500,000 asteroids, so I took 1,000 asteroids and put them on the first computer, or first processor. And on the second processor, which also had a copy of the planets and the sun, I put on the next 1,000 asteroids, and it kept on going right through. So it meant that approximately the elapsed time for the simulation was 500 times smaller than if I put everything on the one processor. Okay, so the first simulation I want to look at is whether Jupiter is a sniper or a shield. So by that I mean, if you have bodies, small bodies outside Jupiter, does Jupiter shield the Earth from all these bodies? And that was the old thinking. Or does it act as a sniper? It funnels the asteroids in and takes pot shots at the sun. So that's what we looked at in the simulation. And other people have done this as well. So I had the sun, the Earth through to Neptune, and I had 500,000 small bodies, and they were on low eccentricity orbits, so orbits that are very close to being circular between Jupiter and Saturn. So I generated them using random number generation for certain properties of that. So I have 500,000 plus I have 7 other bodies. So I have the Sun through to Neptune plus the 500,000 bodies. And I simulated it for 100 million years. Okay, so it's quite a while. So the time step on average was maybe 150 days. So we're looking at 200 million time steps for the 500,000 bodies. So it's a little bit of CPU time there. So I spread it over 500 CPU cores. They weren't run concurrently. I could only get 460 at a time. So the 40 of them sat in the queue there, and they ran afterwards. And that pretty well blew my CPU budget for the year, by the way. So I made sure that I didn't lose that data. It's been stored there in compressed form for a while. Okay, so the parallelism, I put the Sun, Earth through to Neptune and 1,000 small bodies on each processor. And the other thing which I haven't discussed is I varied the time step to try and make the method more efficient. So that time step, I said the average is about 150 days. But imagine you're driving along at 100k and you come up to a corner, you're going to slow down, I hope, to go around the corner. Similar sort of thing happens in simulation. An asteroid is a long way away from a planet, everything's hunky-dory, and as it gets closer it starts accelerating, it starts speeding, so you want to use a smaller time step. If you don't use a smaller time step, for that case, you're going to get an inaccurate answer. Now, you could use a small time step for the whole simulation, but that's a waste when you don't. So a lot of the simulation, when the asteroid is a long way away from the planet, you don't need to use a small time step. You could use it, but you're wasting CPU time. And CPU time is valuable in a large simulation like this. We're always pushing the boundary of CPU time. Okay, so what do you think happened? Any ideas what sort of, I'm talking about astronomical things now. Any ideas? Okay, how many asteroids hit Earth? Any ideas?
Ooh, no idea.
No idea, okay, that's a good answer, I like that.
A million to one.
Million to one, that's not a bad estimate, actually, yeah. Okay, so let's got to stand over here, right? Okay, so the first thing is that 91.08% of the asteroids were ejected. That is a good thing, from my point of view, because it greatly reduces the CPU time. So what in fact happened, and this is quite common, so I had these asteroids between Jupiter and Saturn on low eccentricity orbits, so they're pretty close to being circular, and over, say, a million years, the first million years, the orbits got perturbed by the gravitational effects of Jupiter and Saturn. And it almost always happens when you perturb orbits in this way that the eccentricity gets larger. So it gets pumped up, so the orbits become more eccentric, so they're more likely to go right out into the outer reaches of the solar system. And when the asteroids are on these close to circular orbits, then they're more likely to collide with Jupiter and Saturn and the other planets than when they're on a very elliptical orbits. So why is that? I've got Jupiter going along like this, and I've got an asteroid coming along on an almost circular orbit, so it's spending a lot of time close to Jupiter. If it's on a very eccentric orbit, it's coming in like this, and it doesn't spend much time close to Jupiter. So what happened in the simulation were essentially 3 phases. In the first phase, the orbits of the asteroids are getting stirred up, they're becoming more eccentric, and during that there were lots of collisions. And then after the eccentricity got larger and larger, there were no more collisions essentially, and after a while the asteroids started getting ejected. Okay, so you can see that 5 collided with Earth, which someone said 1 in a million. So my estimate here is 1 in 100,000. That's over 100 million years collided with Earth. Now, that 5 is quite a small number, so it's not a very reliable estimate. It could easily be 7 or 8, so I really need to be running maybe 5 million asteroids or something like that in order to, so that's going to be a bit difficult at the moment. Okay, you can see that Jupiter, large number collide with Jupiter, quite a few with Saturn. Why were there far fewer colliding with Uranus and Neptune? Any ideas? Why is that?
Because they have a larger orbit.
Sorry?
Because they have a larger orbit.
They do have a large orbit, so what does that mean?
So there's like, it's more easy to hit the ones that are closer or have more gravitational pull.
Both points, yes. So gravitational
So they
pull.
don't have much gravitational pull, plus it'll be hard to hit them.
Yeah, because they're far, yeah, that's right.
Yeah.
So that's 2 important things. And the thing that the original question was, is Jupiter a sniper or a shield? And we found that 15.6% got through across the orbit of Earth. So that's about 2 orders of magnitude greater than the estimates from 20 or 30 years ago. The estimates before, computers weren't so good then, so people had to use very approximate techniques. And other people have done similar simulations to us and they've got around 15.6. It's a remarkably constant figure. Okay, now the CPU time. So we've looked at the astronomical aspect. Now we're looking at CPU time. And you can see, so the one processor took just 1.24 days, and another one, the worst or the slowest, is 8.10 days, so 8.1 days. Now that's a ratio of over 6. And I was very surprised at this for the following reason. I would have thought, so remember each processor had the same copy of the sun and the planets, and they had 1,000 of the bodies. And I would have thought 1,000 bodies, small bodies, the asteroids, would have been enough to get some sort of averaging effect. Individual asteroids are going to do something different on the different processes, but on average you would have thought that if I take 1,000 asteroids, at least what I thought, then it'd be similar sort of performance. I was very surprised to see there was over a factor of 6 difference in the CPU. That completely threw me. I spent a week trying to work out why I was doing it. I didn't want to repeat the simulation, so it made it a bit tricky. And what I found, is, at least for 4 of these processes, we have the following situation. Now let me explain this diagram here. This is looking down for the north pole of the solar system, and the X scale is greatly exaggerated compared with the Y scale, so the horizontal is greatly exaggerated compared with the vertical. This is an AU, so there's about 0.6 AU right across here, whereas up here it's about 4 AU. So that means it distorts the orbits. They look elliptical when in fact they are circular. Now this red line here is a snapshot of the orbit of Jupiter, and this blue line is a snapshot of the orbit of an asteroid. And the crosses there mark the end of each step. And every 5th step I've drawn a circle around it. And here, they're starting here. Now the sun is way over here somewhere. It's probably over that far wall over here. Alright, so I think the sun's probably over here somewhere. Okay. So, is Jupiter or the asteroid closer to the sun? Which one's closer? That's not supposed to be a hard question. I just want to make sure I'm understanding. Jupiter's closer, that's right. So if you want to imagine the sun's there, that's fine. So Jupiter's closer. So which one's going to move faster? Jupiter or the asteroid? Jupiter, that's right. As a general rule, the closer you are to the sun, the faster you move. So you can see they started here, and now we get to the 5th step, and Jupiter is caught up with the asteroid. There's still a bit of a gap, but it's got a lot closer than it was here. Now what's going to happen to the asteroid when Jupiter gets close to it?
Small times that.
Sorry? Pulled in, that's right. So if you look at this here, okay, so that's 3 time steps after that circle. The 3rd one is here. So what happens is Jupiter goes past it, if you like, and the asteroid goes in behind it. You get to here, and the asteroid is now closer to the sun than Jupiter. So what happens to the asteroid relative to Jupiter? What does it do? It picks up speed. In fact, it goes into an orbit, a temporary orbit around Jupiter. And it crosses over Jupiter's orbit, and now it's further from the sun, so it's going to slow down. Right? And it gets behind. And look at the time steps here. So this is the distance between two points. So this is the length of time step. When the asteroid is very close to Jupiter here, the time step is a lot smaller. What does that do to the CPU time? Increases it. That's right. And I found that this asteroid did that for 100 million years. Effectively was a satellite. I was very, very surprised. I had never seen this before in simulations. The previous simulation had 100,000 bodies. Nothing like this happened. So that time step is used for all 1,000 bodies in the simulation. You're using the same time step on a given process. So not only was I using a small time step for this asteroid here, it's for all the other asteroids you're using this same time step. So it slowed everything down. And I found that for 4 of the processes this happened, I don't really know what happened on the other three. Everything else, the remaining 493, was pretty normal. Okay, now I'm just going to give you a brief view of two of my work, two of my PhD students are doing. This is work in progress. So the Apollo asteroids, so they're a group of near-Earth asteroids, it's over 8,000 of them. They're Earth crossing. They spend most of the time outside the Earth's orbit, but at one point they do cross the Earth's orbit. So we have potential for collision. And we have the Chelyabinsk, a meteor in February 15, 2013 was an example of a polar asteroid. So Janesse Joseph, my PhD student, is looking at or investigating using in-body simulation the chance of an polar asteroid hitting Earth, and also trying to work out whether the asteroid belt, so between Mars and Jupiter, is the source of the polar asteroids. There's speculation that it is. We're doing large simulations to try to work out whether it's the case. People have looked at individual asteroids, polar asteroids, but no one has looked at the group of polar asteroids. We're using the real data here pretty much. And there's another one of my students, she's been looking at the Kuiper belt. So what's the Kuiper belt?
That's true.
So yeah, so about over 1,700 bodies have been found out beyond Neptune, Pluto being an example. The first one was discovered, besides Pluto, was discovered in 1992. So here we've got Jupiter, Saturn, Uranus, Neptune, and then we have all the bodies out beyond that. And the green dots you don't need to worry about, they're not part of the Kuiper belt. So the question is, what is the long-term evolution of the Kuiper belt? And we're finding that some of the objects out there in the Kuiper belt can get inside Earth's orbit. So they get handed down. So they get matured by Neptune, they get deflected, the eccentricity gets pumped up, they become more eccentric, and then they sort of get handed down to Uranus, Saturn, Jupiter, and then what can happen is that they can work their way back out again. They can oscillate in and out. These simulations are taking a long time. It's difficult to have a lot of bodies because nothing's been ejected. Everything's moving more slowly. Things happen more slowly, and it's quite a pain, in fact, to try and get enough bodies there. And I've worked very hard to try and make the program faster. I'm running out of ideas. And I don't want to brute force it, we're just trying to get more computer power, trying to work out what's going on. And both of these students are under severe deadline because I'm semi-retiring at the end of next year, so I won't be available as their main supervisor. So they're very keen to get things finished by the end. Okay, thank you very much. You've been a good audience.
Questions?
When you said you don't like to lose your data, so what volume are we talking about, and how do you actually store it?
Okay, so no, not a database. I want it also to be readily accessible. So it wants to be at high speed. So I keep it in a compressed state, so it's maybe 5 times smaller when it's uncompressed, and I just store it on local machines because I do a lot of post processing.
So is it what, in a spreadsheet or?
No, it's just in plain text files.
Okay.
So maybe each one might be 1 million lines or something. Yeah, so it's not terabytes, except for the current one where the professor wants me to print out every year. Yes.
In your results slide, why did the percentages overall go up?
How close was it? Probably around the period. Oh, okay, no, I made a mistake somewhere. It's a detail, come on. I actually did find an error when I was checking the slide a couple of days ago, and the decimal point was on the wrong way, so maybe I made another error or something. Thank you for pointing
One
out.
question I had, in the real solar system and the asteroid belt, there are certain orbits that I guess you call them almost forbidden orbits, where effectively a resonance
Yes.
kicks out anything out that
Yeah,
isn't
that's right.
that orbit. And there's sort of the opposite out in the Kuiper belt, where some orbits seem to be actually more stable than
Yes.
others. So do these models
Yeah.
reproduce that?
They do very well at that.
feature?
Despite the fact that we have quite simple mathematical models, they're very robust. They reproduce the essential elements and things. Yes, right.
Are you assuming that the planets are staying constant in their orbit, or are you
rotating into.
No, they're rotating
background
as well. So they will change naturally, so, yeah.
So, I mean, are you sort of looking at the Nice model for?
No, I don't have, the Nice model is starting to lose favour, for whatever reason. Yes?
How did you decide on the start positions and directions and speed?
Okay, right. So, yeah, you just discuss it and decide. No. So with that 500,000 one, so we had a big discussion as to what would be a suitable set of initial conditions for the hypothetical particles, and that will be part of the write-up. So this is like the assumption. What I've been doing in the last couple of weeks, in the last 3 weeks, is just taking 10,000 particles and trying different initial conditions and seeing how much, for example, the number of Earth crosses changes and the number of ejections. And it's actually quite insensitive to the initial conditions. So the model seems to be very robust. It's something I don't fully understand at this stage. Because it's an obvious question I worry about. Yes?
If you do your models though with and without the asteroids, what effect over like 100 million years or a billion years will the asteroids have on perturbing the actual big planets? Do they have any effect at all over?
Yeah, they will. That's right. Now, over 100, let's say you put in, so I've done simulations of 100 million years, in which I had 1,000 asteroids in there, but larger asteroids, and they greatly perturb the planets. But only having 1,000 asteroids is unrealistic. So I have a poor model, and then I get an unexpected result, and it's probably because of the poor model. So you need to have a lot more asteroids in there before you get realistic results. But it can't do that because it takes too much computer time. The people who do galactic simulations have 1 trillion bodies, but they're doing short simulations. When you try and do a long simulation of 100 million years, where the Jupiter's orbit is only 12 years, so you're doing 10 million orbits of Jupiter, round-off error, all sorts of things get at you. And so that problem can't be solved with current computers alone. Yes?
In your model, most of the asteroids got ejected, 91%.
Yeah.
Does that mean that billions of years ago there were a lot more asteroids?
That's the current thinking, yes. Yeah. So the solar nebula model, the Earth stage have a lot more bodies.
So there's a lot of interstellar
Yeah.
bodies out there.
Yeah.
A lot.
Yeah. So if you look at the Minor Planets Centre, there's over 500,000 bodies listed now. There'll be a lot more would be there.
So do these studies come up with an answer for how likely we're to survive the next 100 million years?
Sure. Yes, that's right. So if you look 5 impacts over 100 million years, that's 1 every 20 million years. That's a ballpark figure for what is happening.
But that's likely to be inaccurate, isn't it? Because there's definitely been more than 5 billion in the last 100,000 years.
Yeah, but we're looking at larger asteroids. Yeah, so we're looking at asteroids of the size, say 65 million years ago.
Oh,
Yeah.
Real Earth events.
That's right, yes, that's what I'm looking at the moment. That's why one reason I
So
chose
what
5.
about the 2013 event?
That's a pretty small asteroid, was it? 50, 30
But we're
meters?
not counting those ones, we only counted the big ones.
That's right, yes. Otherwise I would have,
Not the small ones.
Like the dinosaur killer.
yeah, that's right. Yeah, maybe not quite that big, but something like that, yes. So I was actually quite pleased with the fact that on average about once every 20 million years. Yeah, the Earth, as you point out, the Earth does get hit a lot, but the things are quite small. It could be this big. Can't possibly normalize, yes.
so if you have lots and lots of asteroids all over the place, they'd average each other out anyway, wouldn't they?
What do you mean by average out?
Or that their effect.
Yes. But, no, I agree with what you're saying, but so when you take the average, there's still going to be some variation that makes about the average. And the long-term accumulation of that could be some weird. Because when you're doing over 100 million years, I've done some simulation over 1 billion years. So even the small deviation of the average could accumulate. Yeah, you want to ask a question?
Just a comment that you showed an asteroid that was circulating Jupiter, accelerating, going back,
Yeah.
catching up. I believe there's at least one significant sized asteroid that's orbiting Earth.
Yes.
Exactly the same one.
Yes, that's right. Yeah.
So
there's more than one, yeah. It's like a second moon, but the orbit is probably not stable.
Yeah, I just wondered about whether you simulated those and what the stability was.
No.
Because
That's right, I could do that, yes. Other people have done that. But the one I'm thinking of is only stable over about 2 centuries, and maybe others.
So it's just coincidence, it's there at the moment, you'll
Yes.
observe it in.
Yeah, well, there may be others coming through every 1,000 years or
Yeah,
whatever.
but they're not such a collision risk, they're more just orbital.
That's right, yeah.
Thank you.
No, I thought, yes.
Do you think it's possible to rewrite it so you can run it on a GPU?
Yes, I've actually done one simulation. So the simulation in which I had the 1,000 asteroids interacting with one another, I did it for 100 million years, so that was run on a GPU. So I got a speed up to 23
Nice.
compared with running on a CPU. And I had to learn to program a GPU, that wasn't a pleasant task.
One thing they predicted that in the early solar system, I guess the planets actually became unstable in their orbits, and supposedly Jupiter migrated from its original location. Is
That's
these-
the least model, I think, that Grant was talking about.
So that's considered to be pretty good, and are the conditions such that that sort of thing could start happening again, like the long-term stability of the
Yeah,
solar system
okay.
is what I mean.
Right, so the least model, as I said, is losing favour, because the more accurate simulations shown that you can't actually get the results. As for the stability of the solar system, it's close to being unstable, as the current thinking. There were simulations 20 years ago in which people showed that the solar system was unstable over 5 to 12 million years. But if you decrease the time step and got a more accurate answer, the instability went away. So, okay, maybe we could break down this.
Yeah, sure. Before we adjourn to supper down in the Matariki room, I'd like to thank Dr. Sharp again. Very informative talk, and we've got a small gift for our friends.
Thank you very much.
So I'm sure if people could help clear up afterwards as well, we appreciate it.
Yeah.
Thanks very much.